What's up, everybody? Today's video is a collection of course videos from our Llama Fundamental skill track. It covers everything you need to know about working with Llama 3, from fine-tuning the model, querying it, creating structured outputs, and a lot more. If you enjoyed this video, make sure to like and subscribe to this channel. And if you want to go beyond learning and actually practice your skills in the browser, check out the link in the description below.
Welcome to this course on working with Llama 3. This course was created with Imtihan Hamed, a machine learning engineer with 6 years of experience building AI at scale with LLMs such as Llama, so we'll be guided by an expert. Imagine having an AI that can summarize reports in seconds, analyze data, or even assist with code, all running privately on our own machines without sharing our data. This is Llama 3, an open-source large language model developed by Meta. It is designed to understand and generate human-like text and has been trained on massive amounts of data, the equivalent of about 2,000 times the whole of Wikipedia. The model has been released for anyone to download and use through various open-source libraries. For example, Automatic, a company specializing in industrial automation, utilizes Llama models to assist process engineers by predicting equipment maintenance needs. Like other companies and practitioners using Llama locally, they benefit from privacy and security as data doesn't leave their system. Cost efficiency, as they don't have to cover any API costs. And finally, the possibility to modify the model independently. Whether we have a cloud server, an industrial PC, or even just our laptop available with Python installed, we can use the llama-cpp-python library to run Llama locally. To install it, we run pip install llama-cpp-python. When installed, the llama-cpp library can be used as llama-cpp. To start interacting with the model, we need to initialize an instance of the Llama class. This loads the LLM and provides an interface for text generation, allowing to send prompts and receive responses. It has an option to specify the model path, where we pass the location of the saved model file. Llama models are usually stored in gguf format, a format optimized for fast inference. Once we have the LLM instance ready, we can pass it a question. Let's ask, for example, what are some ways to improve customer retention? In the background, the model processes the question or prompt by looking at patterns from its training and predicting the most likely next words to form a response. When we run a completion, Llama 3 returns a structured dictionary response, where the model's reply is stored alongside other information about the model's call. Let's print the full output to see its structure. To extract just the model's response, we access the text field inside the first element of choices, a list that contains one or more response objects. As we can see after unpacking the output, the model suggested some key areas to improve customer retention. Let's continue by exploring how to tune Llama's responses. In the previous video, we learned how to generate basic responses with Llama 3. But how do we control the quality, randomness, and length of those responses? Let's say we are generating product descriptions for different e-commerce sites. Some are targeted at professionals and need to be factual and concise, while others are more lifestyle-oriented and should sound engaging and creative. We can adjust Llama's behavior using decoding parameters to match different tones. These parameters decode or transform raw model output into readable text. By tweaking them, we can change the type of response we receive while maintaining its original content. We'll take a look at 4 key parameters. The temperature controls randomness. Top K limits token selection to the most probable choices. Top P adjusts token selection based on cumulative probability. Max tokens limits response length. Let's see the parameters in action. Temperature values are usually between 0 and 1. If we ask to write a product description with a temperature closer to 0, the output produced will be more predictable. With a high temperature with a value closer to 1, the model will produce more creative responses. Top K limits how many of the most likely words Llama can choose from at each step. If top K is set to a low value such as 1, the model always selects the most probable word, making responses predictable but potentially repetitive. With a higher top K, such as 50, the model has more choices, leading to greater diversity in responses. Unlike top K, which picks from a fixed number of words, top P controls the choice of output words based on how confident it is in its choice. It ranges from 0 to 1. A higher top P lets Llama explore more varied responses, while a lower top P keeps it focused and precise. To limit response length, we use max tokens. This is the direct count of how many words or parts of words, called tokens, should be in the response. If we need a short and precise summary, we can limit the response to just a few words, while if we need a more detailed explanation, we increase max tokens. Let's combine them all together in this example. Setting temperature to 0.2, top K to 1, top P to 0.4, and max tokens to 20 will result in a short, concise product description. We'll get a much more creative output with a temperature of 0.8, top K of 10, top P of 0.9, and max tokens of 100. So far, we've explored how to generate responses with Llama and tune their style and length using parameters. But what if we wanted to refine its tone even more, and maybe even assign it a specific personality? For example, we might be building a customer support chatbot that needs to be used by customers with different expectations. Some users may need a friendly and conversational assistant, while others expect clear, professional answers. We can use chat roles to cater for this. With chat roles, we can guide Llama's responses by defining two key roles in our prompts. The system role sets the assistant's personality and style. The user role represents the person asking the question. These roles can be set as part of our Llama call when using Create Chat Completion. Let's see how it works. Rather than sending just a single prompt as we've done so far, we now need a way to send a structured conversation. The Create Chat Completion function allows us to send a list of messages to Llama 3 with details about the message, which include the system and user role. This is done by passing the list of messages to the messages argument of Create Chat Completion. The system role gives instructions to the model about how it should behave throughout the conversation. For example, let's say we want Llama to act as a business consultant. We define the system role by starting a new dictionary within the messages list. Under the role key, we specify system, and under the content key, we ask the model to behave as a consultant. Next, we need to add a user message which represents the actual question being asked. We append another dictionary with user under role and our question about business strategy under content. Now that we have our structured conversation, we can send it to Llama using Create Chat Completion. The response is returned in a format similar to passing the simple prompt, and we can access it as the first element of choices. However, when using the messages list, we need to access the response with the message key. This contains a dictionary specifying assistant under the role key, as the response is generated by the assistant, and the response itself under the content key. If we want to only access the output text, we'll have to select the message and content key after accessing the first element of choices. In this video, we'll explore how to guide Llama's responses to be more aligned with specific tasks. Even after setting the appropriate parameters and roles, we may find that the responses generated by Llama need further refinement. There are a few techniques we can use to achieve this: refining prompts to provide clearer instructions, leveraging zero-shot and few-shot prompting, and using stopwords to limit unnecessary text. Let's say we're using Llama to summarize industry trends for a quarterly report. Would we ask, summarize key trends in the aviation industry from the last year, focusing on fuel efficiency innovations? Or, tell me about the aviation industry? The first prompt is specific and will be more effective in generating the response we are looking for. To create effective prompts, we should be precise, avoid ambiguity and vague prompts, use keywords, action words, and, if possible, provide examples. When we can't provide an example, we use zero-shot prompting, meaning we give the model a single instruction. It works well for simple tasks, like generating a summary. For example, if we need a high-level report, we might use summarize recent mergers in the airline industry. But when responses need a structured format, we use few-shot prompting by providing examples. For instance, if we want Llama to generate structured aircraft fuel efficiency comparisons, we can show a pattern that includes the aircraft model, passenger capacity, and fuel consumption. Then, we ask the model to continue the entries using the same format. Sometimes, Llama generates long responses when only concise insights are needed. By using stopwords, we can end the response at a specific point. For example, if we're working on a question-answering application for flight tracking, we may want to stop responses before they continue into the next question. To prevent the model from generating output beyond the first answer, we set the stop argument to Q, ensuring the assistant only answers one question at a time, without continuing into unrelated queries. Welcome back to this video on how to structure responses that are standardized and compatible with JSON. Imagine working at a food and beverage analytics company that provides automated market reports to restaurant chains. Instead of manually reviewing sales data and trends, we want Llama to generate structured insights that can be a dashboard's input data. Plain text responses won't work well for this use case, and we'll need structured data that will be processed automatically. Let's look at how we can use Llama to generate structured data that's compatible with JSON. To get JSON responses, we use the chat completions function and specify JSON object as the response format. Let's say we want to see top-selling beverages for the current year. We use the first dictionary in the messages list to set the system role, defining Llama as a food industry market analyst for this task. We then pass the user request, where we ask for our structured data on top-selling beverages. Once we have set up our messages list, we call create chat completion, passing in the messages. We set one more key parameter here, the response format, that we specify as JSON object. This ensures that Llama generates a structured JSON response rather than free-flowing text. The model now returns a well-organized JSON object, making it easy, for example, to integrate the data into an automated reporting system. We can further control JSON responses by specifying a schema, a set of rules that define how the data should be formatted. Let's say we need a structured sales report for food products with specific fields. We can specify this as a dictionary, where type is object to specify the JSON object, and properties are the fields needed, such as the product name, category, and sales growth. This ensures that every response follows the same format, preventing inconsistent data from being generated. So far, we've explored how to generate single responses. We'll now look at how to create a model that remembers previous interactions and maintains context. Imagine an AI assistant developed for a travel booking company that helps customers plan vacations. A user could start by asking about popular destinations in France, then follow up with questions about more destinations, flights, hotels, and local attractions. Instead of treating each query as a separate request, the model should remember what was previously discussed and use that information in its responses. This means we need a structured way to track conversation history and maintain a consistent dialogue, which can be done with Llama by implementing a conversation class. As part of the conversation class, we can store a history of prior messages, adding to the list as the conversation with Llama continues. First, we initialize the conversation by passing in an instance of the Llama model and an option of system prompt. This defines how the assistant should behave throughout the conversation. The system message is stored at the start of the history list. Next, we define create completion, which adds the user input to the conversation history, calls create chat completion to generate a response, and finally extracts the assistant's reply and adds it to the conversation history. With this setup, every new input builds on previous exchanges, and this helps to ensure a more continuous conversation rather than a series of separate responses. Let's have a look at how to interact with our conversation class. First, we load our model and initialize the class with a system prompt, such as ask him to act as a virtual travel assistant helping with planning trips. We then pass a prompt to the create completion method, asking for some destinations in France for a short weekend break. Llama returns some options, and we follow up with another question about destinations in Spain. Because conversation history is tracked, Llama understands the reference to the weekend break and provides a relevant response. You've now reached the end of this course on working with Llama 3. Well done! Over the past chapters, we've explored how to use Llama 3 for various tasks. We started by learning how to run Llama locally using llama-cpp-python, allowing us to generate responses directly on our own machines without relying on external APIs. Next, we explored tuning decoding parameters like temperature, top K, and top P to control response behavior. We then looked at assigning roles within Llama conversations, customizing the assistant's behavior for specific tasks. To make responses more relevant, we guided unstructured outputs using precise prompts, stopwords, and prompting techniques. We also explored structured JSON responses, helpful in formatting Llama's output for automation and data processing. Finally, we built multi-turn conversations, allowing Llama to track conversation history and provide context-aware responses. If you'd like to continue your learning journey with Llama, we have more in store. As part of our Llama skill track, you'll be able to complete a course that takes you through the process of fine-tuning Llama, as well as a hands-on project where you'll use Llama to automate tasks. Welcome to this course on fine-tuning with Llama. I'm Francesca and I'll be your host as we learn how to fine-tune Llama models. Fine-tuning trains an existing model on specialized data to improve accuracy, reduce bias, and expand its knowledge base for specific tasks. The results depend on the quality of the data, the model's capacity, and how well defined the task is. This means that, for the full fine-tuning process, we need a few key components: a training dataset, a model and tokenizer, training arguments, and a fine-tuning class to initiate the training process and produce a new version of the model. The resulting model is then evaluated to ensure it meets the desired performance criteria. To help with this process, we have some useful fine-tuning libraries. We'll start with TorchTune and we'll also briefly cover other options, each with different benefits. By the end of this video, we'll have an overview of the major libraries available and an understanding of the basics of TorchTune, including launching our first fine-tuning task. The TorchTune library, based on configurable templates, is ideal for scaling quickly from experimentation to production. Hugging Face's SFTTrainer provides access to other LLMs, making it suitable for fine-tuning multiple models. Onslaught, with its efficient memory usage, is perfect for setups with limited hardware. Axolotl's modular approach excels when fine-tuning without requiring extensive reconfiguration. TorchTune's standout feature is its recipe-based system. Recipes in TorchTune are modular templates that define the entire fine-tuning process and can be adapted to different projects. We can think of them as cooking recipes for model fine-tuning. They give indications on the step-by-step process, but can easily be adjusted, say, if we want to substitute certain ingredients. This way, TorchTune recipes help keep code organized and ensure it is reproducible. Now, let's go over a basic example of configuring a fine-tuning loop using TorchTune. TorchTune scripts can be run from a terminal or command prompt in an environment where Python and TorchTune are installed. We can install TorchTune using pip install. With TorchTune installed, we can now list available recipes with tunels. If you're using an IPython shell, the command will have an exclamation mark in the front. The output lists all available recipes and includes an additional column, config, that lists the models compatible with each recipe, along with their configurations such as version and memory use. From the list, we can select a recipe and the corresponding configuration file and use tune run to start the fine-tuning loop. This code initiates a fine-tuning loop with all parameters contained in the TorchTune recipe specified. Note that throughout this course, we'll specify that device equals CPU and epochs equals 0 parameters to ensure we keep runtimes to a minimum. However, in most practical applications, we'd set CUDA as the device and epochs to a positive integer, such as 20, to allow the model to train over multiple passes through the data. Let's go over how to pre-process datasets for fine-tuning llama models. When fine-tuning, the results are largely dependent on the quality of the data. Datasets are usually split into 3 parts: the training set, for model training using most of the data, the validation set, a separate set to adjust parameters and select the best version, and the test set, to objectively evaluate the model's performance. The Datasets library by Hugging Face provides a comprehensive collection of datasets for LLM tasks, and it streamlines the process of working with text datasets by providing functionalities for preprocessing, splitting, loading, and efficient memory management. Let's prepare a customer service dataset. The load dataset function retrieves the dataset from the Hugging Face hub and splits it into predefined subsets, such as train. Usually, we'll use this feature to predefine the data's training, validation, and test sets. Once loaded, we can take a look at the dataset's columns relevant to our task, such as instruction and response. Let's inspect the first data point. Each point is a dictionary of column names and values. We are interested in the instruction and response columns for this use case, as they contain the customer service question and target response. To filter dataset samples, we import load dataset and the dataset class. The dataset class stores datasets and provides utilities for converting data to a dataset object. We check the data shape with the shape attribute and filter the first 1,000 elements using Python's list syntax, which stores them as a dictionary of lists. We then convert this dictionary back to a dataset object using fromDict. To prepare the dataset for fine-tuning, we combine the instruction and response fields into a single conversation field. Using a custom function, we format each example as a labeled query and response pair. Then, we apply this function to the dataset using the map method. This ensures the model sees a coherent input-output structure during training. After preprocessing, we save the modified dataset to disk using the save-to-disk method. Saving the dataset locally allows us to reuse it for multiple experiments, including fine-tuning with TorchTune. This step is essential for efficient data handling, especially when working with large datasets. To retrieve the dataset, we can use the load from disk function from Hugging Face's datasets, along with the file path we initially assigned to the dataset. One of TorchTune's features is that it can read Hugging Face datasets directly. After preparing our dataset, we can fine-tune it with TorchTune from the command line by specifying a dataset path and other configurations such as the split to work on, which is usually train or test. In this example, TorchTune takes the Hugging Face dataset file and applies the recipe and configuration. Welcome back! In this video, we'll understand how to configure a fine-tuning job using TorchTune. Fine-tuning in TorchTune revolves around three components. The model includes the base architecture and pre-trained weights, and can be chosen among the different versions and numbers of parameters available. The dataset provides the data to be used for fine-tuning. Finally, the recipe is the configuration file that ties everything together: model, dataset, and training parameters. It can be customized to fit specific fine-tuning tasks, while its format ensures consistency and reproducibility. We've seen how to make our model selection by listing the available models using TuneLS. We've also explored how to prepare datasets to best fit our use cases. Now, let's explore how to set up a custom TorchTune recipe. TorchTune recipes are written as YAML files. Here, the batch size has been set to 4 to ensure efficient use of memory during training on the GPU device, which is specified as CUDA, and the model will train for 20 epochs. All outputs, including logs and checkpoints, will be stored in the directory specified in output there. The model component points to the architecture and model version. In this case, a 1 billion parameter model from the Llama 3.2 series. For optimization, we select a memory-efficient optimizer based on the Adam optimizer. The learning rate is set to 2e-5, a common starting value for fine-tuning large pre-trained models. The dataset is set to Alpaca dataset, a pre-configured dataset. Note that the configurations listed here are only a few of the available parameters. To create and save a custom file in our Python environment, we can use the YAML library to define the configuration as a dictionary and save it in the YAML format. In the configuration, we define parameters such as batch size, device, epochs, and output directory as key value pairs. We use a nested dictionary for the model section to define the pre-trained model architecture we want to fine-tune. Additional components, like the dataset or optimizer, can be added similarly. We then use the YAML.dump method to save the dictionary to a YAML file, in this example saved to customrecipe.yaml. With our configurations ready to go, we can start the fine-tuning process. To do so, we run tune run with our custom recipe file. This command launches training using all the settings defined in our file. After launch, we see informative logs that provide real-time updates on the fine-tuning process. The outputs, such as logs and checkpoints, are all saved to a text file. We also see confirmation of successful initialization of the model and tokenizer. Finally, we see progress updates on the metrics. Here, the training is on epoch 1, step 52, with a current loss of 2.37. The progress bar shows that 52 out of 25,880 steps are completed. This output helps us monitor the training process and adjust parameters if necessary. In this video, we are fine-tuning a Llama model for customer service and evaluating its output. Let's go back to our fine-tuning workflow. To fine-tune Llama with Hugging Face, we'll need 5 essential components. First, the Llama model and tokenizer that we'll use as our baseline. We'll then have a training dataset like the Bitex customer service dataset to provide the model with domain-specific examples for learning. We'll also define training arguments, which configure how the model learns, such as hyperparameters. We'll use the SFTTrainer class from the TRL library to conduct the fine-tuning process. Finally, we'll use Rouge 1 to assess the model's performance and ensure our results meet expectations. First, we load the model and tokenizer from Hugging Face Hub using AutoModel and AutoTokenizer. We set the path token to the end of sentence token to stop token generation when a sentence is finished. Let's configure training arguments using Hugging Face's training arguments helper class. Key parameters include batch size per GPU, per device trained batch size, which controls how many samples to predict on before updating model weights based on the error of those predictions, and learning rate. MaxGrad norm limits gradient values during training to mitigate extreme outlier losses, smoothing learning. Other training arguments can also be configured. To use SFTTrainer, we need to provide the model, tokenizer, and training dataset, along with the column containing text examples, max sequence length for clipping long outputs, and training arguments. We can then call trainer.train to start training. Metrics available for monitoring include the number of training steps it took, describing how many times we updated the weights, and the training loss. We also have some training metrics, how long it took to train in total, followed by the number of samples and steps per second, the number of operations, the training loss, and the epoch. We evaluate our fine-tuned model using the Rouge 1 metric, which measures word overlap between generated and ground truth sentences. To use Rouge 1, we load the evaluate library from Hugging Face, store predictions and references, then compute evaluation scores. The first example matches fully, so it scores 1. The second has no matches and scores 0. Thus, the average score is 0.5. We'll use an evaluation set from the last 500 elements of the BitTeX dataset stored in evaluation dataset. This function tokenizes the instruction text through tokenizer.encode, which converts the text into a list of numerical values that the model actually takes in as inputs, generates outputs with the model with those tokens, and decodes them back to natural text from the list of numbers. We followed these steps by returning the reference and generated answers. Now we can produce the evaluation set by using our preparation function. We initialize our evaluator and run the compute method with our predictions and reference answers. Then we print the results. Let's compare the results of running this evaluation with the original model on the right. We've improved the performance almost 50%. In this video, we explore efficient fine-tuning with low-rank adaptation, LoRA, which helps fine-tune larger models with limited hardware. Training a model goes through a few steps. It involves creating a vector from input data, tokens, multiplying it by a weight matrix, the model, and comparing outputs to reference vectors from training data. The error updates the weights. Larger models need more computation, so reducing model size makes training more efficient. Low-rank adaptation breaks down pre-trained model weight matrices into smaller, low-rank matrices, reducing training parameters while maintaining performance. These smaller matrices can then be trained instead of the larger, original matrix representing the model, which is more efficient since there is less computation required. Reducing the number of parameters this way also acts as regularization, as less granular information can be stored in fewer parameters. This method applies to various tasks and architectures. We can set up LoRA fine-tuning using the parameter-efficient fine-tuning PEFT library. We will use LoRA config to set up our LoRA parameters. The R parameter determines the rank or size of our low-rank matrices. A lower value here reduces the memory usage, while a higher value is a better approximation of the original model. The LoRA alpha or scaling factor determines how much weight to give to the gradient produced by the low-rank matrices when updating the original model matrix. LoRA dropout controls the probability of dropping a layer in the LoRA matrix. Bias sets if we want to train bias parameters or not, whether we want to have a global bias or layer-by-layer bias. The final two parameters are the task types. For llama, this is causal LM, and the target modules, which are the matrices of the LLM we want to run LoRA on. To incorporate LoRA configuration during training, we make a slight adjustment to our training pipeline from the previous video. When setting up the SFTTrainer class, we pass the model, training dataset, maximum sequence length, and dataset text field, along with training arguments and the model tokenizer. Additionally, we include the LoRA configuration under PEFT config with the parameters we've specified. which we defined in the previous slide under LoRA config. We can then initiate training with the train function. Without LoRA, with an NVIDIA A100 GPU with 40 GB of RAM, the largest model we could train was Tiny Llama with 1.1 billion parameters on 11,000 samples in 30 minutes. Any larger Llama variant would essentially run out of memory and would error out. Using LoRA, we were able to fine-tune a variant of Llama 3 pre-trained for chat question answering with 8 times more parameters than Tiny Llama, while using the same dataset and hardware. It trained in about the same time too. Welcome! In this video, we will learn how to make models smaller using quantization so they can be loaded and fine-tuned on a lighter weight hardware. Model quantization reduces memory and improves inference speed by converting models to a lower precision format. Parameters and activations use fewer bits, from 32-bit floats to 8-bit or 4-bit integers, reducing memory usage. We can adjust the training process when we apply quantization so that the effects of quantizing a model have minimal impact on the performance. There are many types of quantization. Weight quantization reduces precision of the model weights. Activation quantization reduces precision in the activation values during inference. Post-training quantization, which is what we will focus on for this course, quantizes models after training to save space. To use quantization, we installed the bits and bytes library via pip. Within our Python training code, we import bits and bytes config. We instantiate the quantization configurations with bits and bytes config, choosing the desired precision, 4-bit or 8-bit, and quantization type, a regular 4-bit floating point, or normalized, which is a form of quantization more resistant to outlier values. By setting the data type for computations with the quantized models, we can control how precise it will be. It defaults to 32-bit floats, but optionally, we can set it to 16-bit bfloat for increased efficiency. This is the full configuration. To load the quantized model with the specified configurations, we use AutoModel for causal LM and try to load the larger Llama 3 8 billion parameter model. To make this possible, we pass our bits and bytes configuration to the quantization config parameter. Now the model weights are loaded using a lower byte representation, reducing memory use with a minor trade-off in output quality and longer inference times. We can use a quantized model the same way as a regular model. Using the Llama 3 chat model we just loaded, we can pass it a prompt with the following text asking about the history of Mars. We can tokenize the text with the encode method and pass our prompter. Then, generate output tokens with the model and our tokenized inputs, limiting the number of tokens to 200. We then decode the generated part of the output by only looking at the output tokens after all the input tokens. Then, we print the result. Seems like a reasonable summary about the red planet. We can't directly fine-tune a quantized model since the weights are discretized. To get around this issue, we can use something we have already learned, LoRA adaptation. We can use the SFTTrainer to pass in a quantized model that we loaded with bits and bytes config, and pass in an instance of the LoRA configs using the PEFT library to PEFT config. Then, we can train the model as usual, with LoRA adaptation using trainer.train. Congratulations on completing this course! You're now well equipped to apply fine-tuning to your real-world projects using Llama 3. You've journeyed through the essentials of fine-tuning, gaining insights into best practices to improve and customize model performance along the way. In Chapter 1, you explored how to prepare datasets, run fine-tuning recipes, and configure them with custom parameters to fine-tune llama models with TorchTune. In Chapter 2, you learned how to leverage Hugging Face's SFTTrainer and optimize hardware usage through techniques like LoRA and quantization to run fine-tuning efficiently. Thank you.